All right, so this video is going to be on organometallic reagents, so specifically reacting with carbonyl groups, so aldehydes, ketones, acid chlorides, and esters. I guess technically carboxylic acids as well, but not the alpha beta unsaturated carbonyls. Those are going to be in a different video. Okay, so we've got our three super common organometallic reagents. So we've got our lithium, magnesium, and copper. Really, the important thing that we want to point out is the difference in electronegativities of these, right? So 1.3, and 1.8. And this is important because what that really does is it creates a dipole between those R groups and those metals. And the R groups, of course, can be alkyl, aryl, allyl, and benzylic. So they are a little bit different in that they can have like those sp2 hybridized carbons, right, bound to the these metals, and or they are the reagent themselves. So specifically lithium and magnesium organometallics, they can have sp carbons as their R group, but the copper organocuprates, they cannot. Okay, they're all carbons, right? And so since they're all carbon containing like R groups, the electronegativity of carbon is 2.5. So that's really what we're looking at, right, when we're talking about the difference in electronegativity, right? So what I can do is actually change the magnitude of this vector in the dipole. Do you guys remember Despicable Me? Oh yeah. So a vector indicates direction and magnitude. So the larger that vector, the greater the difference in electronegativity, or the greater that dipole, right? So the more polar bonds, like lithium and magnesium, are going to be more reactive than the copper like the R group and the copper. Their difference in electronegativity isn't as great, and so the copper, turns out the copper is pretty lame, or awesome, depends how you look at it. It's kind of selective in its reactivity because it's not very reactive with respect, or I guess in comparison to magnesium and lithium. Okay, just to give you the names when we talk about it, the organolithium reagent. The magnesium is a Grignard reagent, and then organocuprates is what we'll call those copper compounds. Okay. Notice also the difference between the copper and the lithium and magnesium, where that they had two R groups on it. Even though we're only using one, it's got two on there. Okay. So preparation of the lithium, the organolithium, the Grignard, as well as the organocuprate. Okay, it's pretty straightforward, intuitive, and I think we'll be good on this. We know how to do this already. We can just think about it a little bit. We're going to use elemental lithium and magnesium in order to make these. So think of it. Notice I'm using the fish hook arrow. I like to think of it as each lithium gives each of these things, the R and the X, an electron. And there was also an electron in each of our two electrons in that chemical bond. And so if we kind of do a homolytic cleavage, split it up, give an electron to R as well as X, and then an electron from each of those lithiums makes them both anionic. Okay. Really, you don't need to know that. I mean, this is the way my brain thinks of it. That's kind of the way it is actually. They reduce because they're elemental metals. So they give an electron, make an R minus, make an X minus, and then there you go. You get your salt as well. Here's a methylethyl bromide, bromobutane. And then you get butyllithium, right? So butyllithium is super common organolithium reagent. And so I just want to show you how to do that. It's actually like pyrophoric as well. If you shoot it into the back of a hood on a paper towel, it will burst into flames. So kind of awesome. These magnesium reagents, these aren't as reactive as I told you, and so those aren't going to burst into flames, but they can, depending on what you have, what you're working with, right? So you still got to be super careful with these. And magnesium is actually in group 2, so it is dicationic, and so it actually gives up 2 of its own electrons rather than having like the 2 lithiums, right? So you end up with a dicationic magnesium that satisfies the charge on the R minus and the X minus. Okay, so an example would be bromobenzene with magnesium. Throw 2 electrons at it, get your phenyl minus and your bromide, and there you go. There's your Grignard reagent. So these processes aren't too bad. The the organocuprate is a little bit different. Notice it has that lithium in the formula, so that can help us remember that we make it from an organolithium reagent. Remember, and then we also make it, of course, with copper iodide. It's got 2 R groups, so we need 2 of those organolithiums. Copper is going to be plus and iodide minus. And so splitting these guys up as well helps us understand really how this works. So the R minus can attack that copper. It's a positive charge, and we got a negative R, right? So attack that. It's neutral now, right? And we have a lithium iodide salt. Well, we've got another organolithium reagent, so attack again. And if you have a negative charge going into a neutral situation, then you're coming out negative, right? So negative in, negative out. And so we've got our organocuprate now, and that lithium is now the countercation for the copper that is negatively charged. Okay, so here's a practical example. We have 2 methyl lithiums and a copper iodide, and we get our dimethyl organocuprate. Okay, and that's pretty much it for the preparation of these guys. So the examples are very simple because it is simple, but it's going to take some practice just so that you get to the point where it is just kind of second nature and you don't have to put any thought into it. Okay, but moving on to acetylides. So we've seen acetylides before, pKa of 25 for those alkynes because it is an sp hybridized carbon, and so it's a little bit more stable than your sp3, right? And so that is an acidic proton, and in the presence of methyl lithium, for example, that methyl is a very, very strong base. And so what's going to do is rip off that proton. And that's actually what a lot of organolithium reagents are useful for, like butyllithium, really strong base, just swoops on acidic protons left and right. Okay, so and then I wrote the pKa's for you just so you know that you always form the weakest base, right? Or I'm sorry, weakest acid and weakest base. And so that's how we're forming acetylides. We can use these as nucleophiles. We've already done this before, just kind of throwing it at you again though, right? And of course, to remove that proton, you can use sodium amide and sodium hydride as well. All right, so let's say we've got our organolithium and we've also got our Grignard. Okay, so these are sources of R minus, right? And so, like I just said, with the methyl lithium, these are strong bases, and so whenever you're reacting with your desired organic compound, you have to be careful because it's going to remove acidic protons first and foremost, right? And so if you have alcohols or carboxylic acids present, then it's not going to work out for you. Okay, so, and we'll see how to kind of circumvent that issue in a little bit with protecting groups, but first let's kind of look at them as nucleophiles, and then we'll see really what I'm talking about. So these guys react with carbonyl compounds. That's the topic of this chapter, right? Shocker. So the propyl lithium, make sure you're labeling the number of carbons for these kind of these organometallic compounds, because oftentimes you lose carbons, and I don't want that to happen, because I don't want you to get it wrong just for that. That's silly. So label them all out, attack the most electrophilic site, which is the carbonyl group, of course, right? And then I like to, again, label it out just so I keep track of all my carbons, right? You got to do inventory. Protonation of that alcohol, or sorry, that O minus, the alkoxide with water gives you the alcohol in the end. And notice this ketone went to a tertiary alcohol. That's going to be a common theme. let's say we had this guy with an alcohol on the end and we had our propyl lithium, okay? It's going to grab that proton first and foremost, and then you end up with the alkoxide. You also get your propane, right? And so that's why these reactions are highly pyrophoric, because propane is used for fire, right? And so if you have an exothermic reaction occurring, it's reacting with water, creating propane, which is a good source of energy, right? Then you're just kind of, that's where the fire starts, okay? So taking a look at this carboxylic acid, it is a carbonyl group, right? So let's throw out organolithium reagent, see if we can get that addition to it. But bummer, pissed, because it's got that acidic proton. So it's just going to remove it to form the carboxylate. Okay, so just keep an eye out for those acidic protons, and you'll be all right. Okay, so again, these guys are nucleophiles. They're very strong. They're also very strong bases. So look for the most acidic proton, but also the most electrophilic site, and then you should be good to go in terms of where these things are going. I did tell you that the lithium can have an sp hybridized carbon attached to it. So we have formaldehyde getting attacked by this alkyne, acetylide, right? That's your source of acetylide. And so once it does that, you end up with this alcohol. So again, I like to make sure I label all my carbons 1, 2 with the triple bond there, and then 1, 2, 3 coming off of it. So that way I don't lose anything, and I make sure I got the desired product. Okay, pretty straightforward, right? Notice the versatility and like what you can actually end up doing. So now this our OChem game is going to be solid, because our synthesis game, we got this alkyne here. Now we know how to do alkyne reactions. We can do all kinds of stuff with that. And so using organolithium or Grignard reagents or organocuprate reagents, these are solid tools here for synthesizing our desired compounds. So although there are more reagents to kind of understand how and remember, they're adding to our skill level for sure, increasing the opportunity to make a huge amount of organic compounds. And so it's just going to be it's like a little bit more difficult because there's more stuff, but it's also making synthesis way easier because there's more stuff. So how can we actually make or do the reaction on this compound if we really want to hit up that carbonyl group? So we're going to use a protecting group, and it's specific to alcohols. And so we're going to use imidazole, which is this guy right here. It's a little heterocyclic ring. You should ask yourself which nitrogen would remove that proton out of those two nitrogens. Look at the conjugate acid and then see which one is more likely to grab it. Okay, so you want to see which one is more stable, right? Because it's going to be bearing a positive charge. We also got this TBDMS chloride. It's the tert-butyl dimethylsilyl chloride. Sorry, silyl. So once you do that, it basically just removes the proton. It attacks, you lose the chloride, and then you get this silyl group on the oxygen that was the alcohol. Now, this guy is not susceptible to to reacting with base or strong nucleophiles. So the butyl lithium in this case will attack selectively the carbonyl group. Okay, and so that's what's happening. I'm not going to draw the second step where we protonate it. I'm just going to go straight to the product. But now, since we have that protecting group on there, we don't really want it there, so we have to do something called deprotection. And to deprotect this silyl ether, this is what it's called. This silyl ether will be removed. It reacts with fluoride salts. So super common one is tetrabutyl ammonium fluoride. And then you end up with your desired compound in the end, right? You get your alcohol back, and you also get this this SIF bond right here. That's what's happening. It's really just attacking the silane or the silicon, and then there you go. You get your desired compound. So if you do have an alcohol that would be reactive, what you want to do is protect it first with the silyl ether. Okay. All right. So the last portion is going to be on reactions of organometallic reagents with carboxylic acid derivatives, right? So specifically acid chlorides and esters. And again, as I stated in the beginning, the organolithium and the Grignard reagents are more reactive than the organocuprates. And so what we're going to do is go over the reactions with the organolithium and Grignards first, and then we'll go over the organocuprates. Okay, so let me do a not generic version of this. So we have an acid chloride and we react with methyl lithium. Okay, now of course insert R group, right? You have your imagination. Think about whatever you would want to put on there and then throw it on there because they're pretty versatile. So we've got our nucleophile attacking the carbonyl group, because that is the most electrophilic site. The electrons go up to oxygen, then back down to kick out that good leaving group, chloride. Okay, so we do have a ketone now, but remember these guys are very reactive. Okay, so another methyl lithium can come along and react. Can't stop, won't stop, y'all. Okay, we got to keep going. Yeah. Nobody can stop it. It's just plain and simple, y'all. Okay, so methyl lithium attacks the carbonyl carbon again. Get the alkoxide, hit it with a little water to protonate it to end up with your tertiary alcohol in the end. Okay, so this, it's very easy, right? Very straightforward. The only tricky part is that you just have to remember that the organolithium and the Grignard reagents are very reactive, and if you have an acid chloride or an ester, you're going to get a tertiary alcohol. Okay, whereas before, if we had like an aldehyde or I guess in aldehyde, you would end up with you only attack once because you don't have the leaving group, and you end up with a secondary alcohol as opposed to the ketone, where it is a tertiary alcohol, but you're still only reacting with one organometallic. Okay, so here's an example of reactions with an ester. So I drew this weird looking one just so you understand that it's gonna work still. It's just broken down, still an ester reacting with an organometallic, Grignard specifically, and so you add two phenyl groups because that phenyl group attacks the carbonyl and then it kicks off that alkoxide. So I'm going to abbreviate the cyclohexane ring with the CY. And then the benzene ring is obviously the pH, the phenyl. So we end up doing the same mechanism, right? You kick off that alkoxide, you end up with your ketone, and then you attack with another equivalent of benzene or phenyl magnesium bromide, that Grignard, and then you get it protonated, eventually getting to your tertiary alcohol in the end. Okay, so again, same mechanism. So you guys are stoked because it's easy. You guys got this. Chill. Okay, so I'm just gonna draw out all the salts that form because I know some of you like that. So the hydroxide would be after the water was added and it protonated, right? So that forms a salt with magnesium. We also have the alkoxide forming a salt with magnesium. And there you go. Desired product, some salts, boom. That's it. All right, so let's take a look at acid chloride, but with an organocuprate. Okay, so if we have again, we do have two R groups on that copper, but we're only using one of them. Okay, so it's kind of weird. It's counterintuitive, right? So if we hit that acid chloride with the organocuprate, we can stop and we has to stop because copper is lame. Okay, so we make this ketone, and that's it. We stop there. And that's again because the difference in electronegativity between copper and carbon isn't as great as it is with lithium and magnesium. And so it's basically less anionic. It's less nucleophilic of a carbon, and so it can't react with the carbonyl carbon in a ketone or an aldehyde. It really just reacts with your acid chloride. Okay, don't even touch the ester. It's a super bummer, but it's also kind of cool because it's selective, and you just straight up add that propyl group to that acid chloride, and then you got your ketone. Okay, so it's very similar to Dibol and the lithium aluminum hydride chicken foot. Remember those guys reacted with acid chlorides to get the aldehydes, right? So hit it with Dibol and water, and you get your aldehydes selectively. So in the same sense, it's very similar. You can keep those guys in their own category where they're only adding one equivalent of the nucleophile and not completely just attacking that carbonyl again and again. All right, so that's all she wrote. Have fun. Let me know if you have any questions.